John Dalton was actually a really influential chemist around the turn of the 19th century. In the early 1800s, he did a lot of work, and some of them were with gases. And one of the really cool things that Dalton did was he came out with this idea of Dalton's law of partial pressures. When we're breathing in air, like right now, it's actually more than just oxygen. The air we breathe is roughly 20% by mass oxygen, roughly 80% by mass nitrogen, and there's also a little water and some argon and stuff like that in there. But anyway, Dalton realized then that the total pressure you experience is the sum of the individual pressures. So you can see down there in the picture that you have three different gases. This one's about 300 kilopascals, which is a type of measurement. This is about 600 kilopascals. This is about 450 kilopascals. And if you put all of those gases together, and that's what's happening in the right-hand flask, the sum of those three numbers is 1350. So the total pressure is just literally the pressures of the individual ones, and this will be helpful for us. So the pressure we experience, about 1 atmosphere at sea level, about seaside, whatever, that's going to be a combination of nitrogen plus oxygen, of course, a little water, stuff like that. Kind of cool. So here's a reaction where diborane, B2H6, is reacting with oxygen to make boric oxide, B2O3, and water, all right? But before we go into the details, notice that everything in that reaction is a gas except the boric acid, B2O3. That'll be important. So anyway, we're mixing B2H6 and O2. We're mixing them in the correct stoichiometric ratio. So what that means is there's going to be 3 moles of O2 for every 1 mole of B2H6. And the total pressure of the reactant mixture, 200 millimeters of mercury. So the question is, what's the partial pressure of the reactant gases? Okay, so the total reactant pressure is 200 millimeters of mercury. And you can see from that equation that you have 1 diborane, 1 B2H6, and 3 oxygens, 3 O2s. So there are a total of 4 moles of reactants. And if the total pressure is 200 millimeters of mercury, then 1/4 of that will be B2H6, because there's a 1 in front of it, and 3/4 of 200 will be the O2. So when you take 3/4 of 200, you get 150, and 1/4 of 200 would be 50. So those are the pressures of the individual gases. And again, how we did that, we just added the moles. So there's a total of 4 moles gaseous reactants, okay? And those 4 moles, if this has been a stoichiometric ratio mix, then 1/4 will be the B2H6 and 3/4 will be the O2, which is kind of a cool thing. Now, B2O3 is a solid, so if this was a ratio based on the products, you wouldn't include the solid. This only works for gases. That's what Dalton's law is all about. We ignore solids and liquids when it comes to pressures, at least 99% of the time. This becomes important when you collect a gas over water, because water actually has a little bit of pressure at almost all temperatures. This is liquid water, by the way. So for example, if you want to figure out the total pressure of a system and you're collecting hydrogen, then that total pressure is going to equal the pressure of water plus the pressure of the hydrogen gas. And a lot of times you only want the pressure of the hydrogen gas. So you can look up in tables what the vapor pressure of water is at different temperatures. It goes up as the temperature goes up, because pressure and temperature are proportional to each other, etc., etc. But the pressure of water at each temperature is known pretty accurately. So if you have a total pressure reading, which is usually what you measure in the lab, and you know what temperature your water is, then you can subtract the pressure of the water to find the pressure of your gas. This is Dalton's law, which is pretty cool.